Hello, Professor. Today I want to introduce lecture full summary. I am today's presenter, Jiajun Jiang. Here's the agenda. We're gonna start with introduce ALU and the number representations, side representations, and real numbers, and adder, multiplier, and divider. And ALU is arithmetic logic unit. The ALU get the output code from the instructions, so the ALU knows what kind of instruction is. The left part in the slide is the number of ALU control lines to decide which arithmetic is. The ALU inputs can be 2 registers or 2 integers or even 1 register, 1 integers. And the multiply in the computer is add many times. And how to represent number in computers? There's many different categories. We can see the picture. The number in computer can divide to integer and floating points. The integer can divide to sign represent and unsigned represent. And sign represent, we have so many methods to represent the sign number, like the sign and magnitude, 1's complement, and 2's complement. And we use 2's complement nowadays. And how computer represent positive and negative numbers? The first one is sign magnitude. The sign magnitude, the most significant bit is the one to decide this is a positive number or a negative number. So when a number is 1 means negative, 0 means positive. And the range of number we can represent is 2 power of n bits. So if we have 8 bits, it's 2 power of 8 minus 1. Because in sign magnitude, we have 2 ways to represent minus 0 and 0. So this is why we have to minus 1, because we have 2 0 in sign magnitude. And here's the example, the 1, 0, 1, 1, 0 in sign magnitude. We can see the leftmost bit is 1, so this is a negative number. And 0, 1, 1, 0 is 6, so this will equal to minus 6. And then is 1's complement. The way to represent the positive number is just same as the sign magnitude, but the way to represent negative number is we have to flip the 0 to 1 and 1 to 0. And 1's complement still have 2 ways to represent 0, which is pretty bad. So here's the example. We can see the 6 in positive is 0, 1, 1, 0 is just fine. But the minus, we just flip the 0 to 1, 1 to 0, so the minus 6 will be 1, 0, 0, 1. The 2's complement is pretty good right now, and the way to present the positive number is just same as 1's complement and sign magnitude. So we can see if we want to present the positive number, there's no difference between 2's complement, 1's complement, and sign magnitude. But the way we want to present the negative number, we have to flip 1 to 0, 0 to 1, just like 1's complement. But we have to add 1 in the last. So the pros is there's only one way to represent 0, which is all the bits is 0. And the range of number is 2 power of bits. And the example is we can see it still have 6. The positive number represent is just same as 0, 1, 1, 0. But the negative 6 is we flip the 1 to 0, we got the 1, 0, 0, 1, and we have added 1 on the rightmost bit, so we get 1, 0, 1, 0. And then is exists. The leftmost bit still is represent negative or positive. And the way to represent the negative number is we use 2's complement and add the largest number. And the example is 6. The 6 in binary is 0, 1, 1, 0, and we have to add the largest number, which is 0, 1, 1, 1. So it will become the 1, 1, 0, 1. And the minus 6 is 1, 0, 1, 0, and we still have to add the 0, 1, 1, 1. So we will get 0001. and is subtraction of binary numbers. The computer used add a negative number to represent subtraction. For example, if we want to 20 minus 10, in binary we will say 0, 0, 0, 1, 0, 1, 0, 0, add the minus 10, which is 1, 1, 1, 1, 0, 1, 1, 0. So we will get the 1, 0, 0, 0, 0, 1, 0, 1, 0. So this is how to subtraction in binary numbers. Fixed point is to present an integer and its fractional parts. The integer part will just be assign the sign represent, and the fraction part is we can see I already write on the right side of the slide. The 0.5 is equal to 0.1, and the 1 in binary is equal to 2 to the power of minus 1. So there's a list on the right side we can see. And the example is if we want to present the 20.125, the number in binary will be the 10100.001 because the 122 on the fractional part is equal to 001 in binary. The floating point number, when we want to use the floating point number, which means the number is very, very big or very, very small. And the way to present the floating number is we have two type of. The first one is single precision, and the second is double precision. The double precision means can contain the larger number and smaller number than the single precision one. And there's is the formula underneath the slide. The first one bit still represent the sign bit, and the 8 bit is represent exponent bit, and the last 23 is fraction part. And here's the example. If we want to use IEEE to present the minus 0.75, so we have to transfer from decimal to binary. First, we ignore the negative sign, so it will be minus 0.11, and we can write to equal to minus 0.11 times 2 power of 0, and it will equal to minus 1.1 times 2 power of minus 1. So the way is when we get the 1 point blah 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 blah, like the blue part, and we can see the minus 1 on the 2 power of minus 1, we have to make the number add 127 because its BIOS is 127. So we already got all the information we want. The first bit is side bit. So this is negative, so this is 1. And we put the purple part is 126. So the 126 in binary is 0, 1, 1, 1, 1, 1, 0. And the 1, the blue part, is just the rest of them. And then is adder. The hefter adder is pretty simple. We have 2 inputs and 2 outputs. We can see the truth table. I already write down. When the A, B is 0, the carry and the sum is 0. When A and B, there's one of them is 1, the carry is still 0, but the sum is 1. But when they are both 1, the carry will be 1, the sum will be 0. The full adder is just same as the half adder, but we have 3 inputs. And the truth table represent if we have 2 or more over 2 inputs is 1, the carry will be 1, and the sum will be 0. But if we have 3 of them is 0, 3 of them is 1, the carry and the sum will be 1. The ripple carry adder is we put the 1-bit full adder m times, so we can get the m-bit ripple carry adder. And the ripple carry adder is simple, but the delay is pretty long because we can see the picture. When the 0 and A0 B0 coming, we have 3 input, and we have to wait till the adder is finished, is calculated. So we get two output. The first output is sum, and another one is carry. So the second adder have to wait the first adder's carry, so the second adder can get all the information it wants. So we have to wait like a chain. Second have to wait the first one. The third have to wait the second one. So the circle path delay will be pretty long. The carry select adder, the main point for the adder is because the repo carry adder, the delay is just too long. So the carry select adder, one set will predict the carry will be 1. Another set will predict the carry will be 0. So when the incoming carry is known, we just select the correct set without the waiting. So it will decrease the waiting delay. The carry look ahead adder, the truth table is just right side of the slide, but I already conclusion the right side of the truth table become the left side. And the first one conclusion is when two inputs are both 0, the Cout must be 0. And the second is when the two inputs are both 1, then the Cout must be 1. And the third is when A or B, one of them has 1, then the Cin will equal to Cout. So the truth table, we can see the AB both 0 is a kill. And if one of them have 1, so it's a propagate. And if they both 1 is a generate. When we see the formula, we can see if we want to find the I bit, does it have a carry? We can see from the I bit and the 1 before the I bit. So we don't have to, like the repo carry adder, have to wait till the previous adder give the carry. Carry step adder is when we want to add a lot of operands, like over 2 or 3 or even more. This adder can reduce the delay. And the 3 step is compute the sum and ignoring the carry, and then is compute carry separately and add the sum and carry. And we can see the example here. We add the ABE and we can get a C and S. The C1 is the carry and the S is the sum. And we add the S1 C1F and we get the S2 C2 and we add them together. Use the traditional adder, we can get the final result. So we can assume if 1 bit adder, the time delay is 2t. When we use 4 bits adder and use traditional method, we need 14 times delay. But when we use carry step adder, we only need 12 times delay. When the operand is become more, the reduced time delay can be more significantly. And is multiplier. The multiplication in unsigned binary, if we have n bit unsigned multiply n bit, we will get a m plus n bit number. But if the number n bit and n bit is signed bit, the total result will be n plus n minus 1, because we still need 1 bit to represent the signed bit. The 0 multiplier is easy, but it still have a lot of time delay. It consumes a lot of time. And the right bottom picture, we can see there's a picture to present how the 0 multiplier works. But the algorithm is 4 steps. The first one is test the multiplier first bit. If the first bit is 1, we add the multiplicand to product and place the result in product register and go to step 2. If the first bit of the multiplier is 0, then go to the step 2 directly. And the step 2 is shift the multiplicand register left 1 bit, and then we shift the multiplier register right 1 bit. Check the circle. If we do the repetition 32 times, means the multiplication is done. If we are not done 32 times, we go to step 1. The boost algorithm is when we want to use to add the very, very large number. It will be very useful. So how to do the boost algorithm is we have to add a 0 on the rightmost bit and determine the first bit and the bit we add. So if they are 0, 1, so add multiplicand and shift. If they are 1, 0, so subtract the multiplicand and shift. If they are 0, 0, we do nothing. And if they are 1, 1, we do nothing. And if when we right shift, we just keep the sign bit. If the sign bit is 0, we just add 0. If it's 1, we add 1. And this is very good when the number have a lot of consecutive 0 or 1, because we don't have to do anything, we just shift. But it is very bad when we encounter alternating 0 and 1 in the multiplier, so we have to add and shift and subtract shift, so it will consume more time than the traditional one. And then is divisor. The picture show how the divisor do, and the algorithm for the divisor is, first step is the computer doesn't like the human, so the computer cannot predict the remainder is bigger or smaller than the divisor. So the first step, we have subtract the divisor register from the remainder register and place the result in the reminders register. And then we have to test the remainder. If the result is positive, means the divisor is smaller or equal to divisor. So we have to add 1 in the quotient. If the result is negative, we have to restore the original value by adding the divisor register to the remainder register and place the sum in the remainder register. Also, we have to shift the quotient register to the left, setting a new less significant byte to 0. And then we have to shift the divisor register right a 1 bit. And then we have to check we do the circle 33 times. If we do the circle 33 times, means the division is done. If it's not, we have to start from the first one step. And this is all my summary. Thank you, Professor.